This is Bill Farmer. Welcome back to Software Engineering 2FA3. Today we're going to continue with the topic of Turing machines and computability. Today, specifically, we're going to talk about the great limitation theorems. So the great limitation theorems are theorems that show the limits of what can be done with logic. And there's four of them that I'm going to present. The first is called the first incompleteness theorem. This is one of the most famous theorems in all of logic, maybe the most famous theorem. And it was published by Kurt Gödel in 1931. It says that no consistent, recursively axiomatizable, sufficiently strong theory can prove all the truths of natural number arithmetic. So let me explain what these different components mean. So if we have a theory, and the theory is consistent if it's basically free of contradiction. You can't prove a false statement from it. It's recursively axiomatizable if there's an algorithm that will tell us whether a given formula is an axiom or not. And it's sufficiently strong if the theory is strong enough to talk about natural numbers and lists and things of that kind. So basically what it says, if the theory is consistent, won't prove falsehoods. If it's recursively axiomatizable, we can tell what is an axiom or not. And it has a little bit of strength to be able to prove things about numbers and lists of numbers and so forth, then it won't be able to prove every true formula about natural number arithmetic. That it will be incomplete in that sense. So that's the first incompleteness theorem. Gödel also proved at pretty much the same time the second incompleteness theorem. This says that no consistent, recursively axiomatizable, sufficiently strong theory can prove its own consistency. So if we can write down in a theory a statement that says this theory is consistent, we will not be able to prove it. Now we might be able to prove this formula in a stronger theory, but that doesn't really help us much. If we're trying to figure out if our given theory is consistent or not, we'd like to be able to prove that's consistent. If we have a theory that's consistent, recursively axiomatizable, and sufficiently strong, we can't prove in that theory that it's consistent. We can only prove it's consistent in a stronger theory, and then that begs the question, is that stronger theory consistent? So that's the second incompleteness theorem. The third limitation theorem is the undefinability of truth theorem, proved by Alfred Tarski in 1933. It says truth cannot be defined in a sufficiently strong theory. So if we would like to make statements about truth in our theory, we need to define what truth is. We cannot do it in a sufficiently strong theory. We could define truth about our theory in a stronger theory. So again, we get to the same kind of problem. If we're proving, we can talk about truth in a stronger theory about this theory, but we can't talk about truth of the theory in itself. And the fourth limitation theorem is the undecidability of first-order logic. This is due to Alonzo Church in 1936. So basically what Church showed is that there's no algorithm to be able to determine whether a given formula of first-order logic is valid or not. So these are three very important theorems. Notice they were all proved in the 1930s. In the 1930s, this was a major shift in logic and in how people related logic to mathematics. Basically, everything changed in the 30s. Okay, so I have a question for you. The great limitation theorems state that there are limits on what can be A, proved, defined, or B, defined, C, computed, and D, all of the above. So think a moment and determine what you think is the right answer. Okay, thank you for considering this question. The answer is D, all of the above. If we go back to these four limitation theorems, the first two are about what can be proved, and the third is about what can be defined, and the fourth is about what can be computed. So now I want to look at a theory, Robinson Arithmetic. This is a very simple theory. The signature of it, which I'll call sigma, it has a constant symbol 0, a unary function symbol S for successor, and binary function symbols plus and times. So this is a signature for natural number arithmetic. And we're going to let gamma be the following formulas. The first says that 0 is not the successor of anything. The second says that the successor function is injective. The third says that every member of our domain is either 0 or it's a successor of something. And the fourth and fifth are the normal recursive definitions for plus in terms of successor, and the sixth and seventh are the ordinary recursive definitions for times in terms of plus. So this theory, which we are traditionally called Q, it's a first-order theory. It's called Robinson Arithmetic after the person who invented it, Raphael M. Robinson. This theory is very simple. It has just 7 axioms. It's a theory of natural number arithmetic. But it is you can think of it as a sub-theory of first-order piano arithmetic. This is a much stronger theory that we've looked at previously. This theory of first-order piano arithmetic has the induction schema, which is an approximation of the induction of the weak induction principle for natural numbers. Now, axiom 3 is used in place of the induction schema. So axiom 3, it says that if you think of it as natural number, every natural number is either 0 or it's the successor of something. So this is a very weak replacement for the induction schema. And because this theory is so weak, it is so weak because we don't have the induction theorem, and because it's so weak, there's a lot of things we cannot prove in this theory, a lot of basic facts about the natural numbers. We can't prove the associative law, commutative law, and distributive law about either plus or times, and we can't even prove that for all x, the successor of x does not equal x. So none of these are logical consequences of Q. And the interesting thing is, each instance of these laws is a logical consequence. So I can prove that 2 plus 3 equals 3 plus 2. Or I can prove that 3 does not equal 2. Now, when I say 2, I'm really thinking of 2 equaling the successor applied twice to 0, and 3 is the successor applied 3 times to 0. So anyway, I can prove every instance, but I can't prove the general statements in this theory. And the first 3 limitation theorems apply to Q. Since Q is very likely to be consistent, it's a very simple theory. It's hard to imagine how it could possibly not be consistent, but we can't really prove in Q that it's consistent. It's recursively axiomatizable. Since it only has 7 axioms, you can easily write a program that can recognize when an arbitrary formula is one of those 7 axioms, and it is sufficiently strong. Now, how do we know it's sufficiently strong? Because when the Q was discovered by Raphael Robinson because he looked at Gödel's original proof of the incompleteness theorem, and he basically said, what is the minimum strength that a theory needs to be able to make that proof go through, and he came up with Q. Q is sort of the simplest theorem that the first incompleteness theorem applies to. So it is sufficiently strong. Now, Q also illustrates the fourth limitation theorem because it is an example of an undecidable first-order theory. So Q is very useful as an illustration of or making these four limitation theorems concrete. So I'm going to give some metatheorems about Q. What a metatheorem is, it's a theorem about Q. It isn't a theorem of Q. So a theorem of Q would be some fact that we could prove in Q about natural number arithmetic. Metatheorems are theorems in the meta language of Q. They're theorems about Q. So we're going to look at some of these metatheorems. The first is Q is finitely axiomatizable. That's obvious, has 7 axioms. So for that reason, it's recursively axiomatizable. Q is incomplete. Incomplete means that we can't, there will be some statement that we can neither prove it nor its negation. And not only is Q incomplete, but we can't make it complete by adding more axioms. Every consistent, recursively axiomatizable extension of Q is incomplete. So if we add more axioms, the only way we can make it complete is we have to add so many axioms that there will be no possible way of recognizing what is an axiom or not. There will be, in other words, no computer program that can tell us what is an axiom or not. So we say then Q is essentially incomplete. Consistency is not provable in Q, nor is it provable, nor is consistency, nor can we prove consistency in any consistent recursively axiomatizable extension of Q. That's because Q is sufficiently strong, and any consistent recursively axiomatizable extension of Q will also be consistently strong. Truth is not definable in Q. That's because Q is sufficiently strong. Q is undecidable, and every consistent extension of Q is undecidable. Undecidable means if we take an arbitrary formula, there's no algorithm that will tell us whether an arbitrary formula is valid with respect to Q or not. And every consistent extension of Q is also undecidable. So Q is what's called essentially undecidable. We can't make it decidable by adding more axioms. And we can also use Q to define what it means to be sufficiently strong. We can say a theory is sufficiently strong if Q can be embedded in that theory in some way. So that completes my discussion of the great limitation theorems. Next time we're going to be talking about the most important subject of this topic, Turing machines. See you then.